So we are now going to start up a new chapter, that is equilibrium rate and reaction. Okay, the chapter name is reaction rate and equilibrium. So basically, this chapter is all about, in this chapter, we are going to understand first about the effect of concentration on the reaction rate. So basically, we will study about the reaction rate. By reaction rate, it means how fast or slow a particular reaction is there. Suppose in a reaction, we have reactant and they convert into product. So reactant, when converts into product, they require some amount of time. Okay, so some reactions takes place very quickly, some reactions take place very slow, and some reactions are moderate. For example, if I say reaction of sodium with with oxygen, it's a very fast reaction. If I say rusting of iron, it's a very slow reaction. And if I say KMNO4, any lead acetate, if it reacts with Ki, it will convert into PbI2. So this reaction is a moderate reaction, not too fast, not too slow. So some reactions are very fast, some reactions are moderate, and some are very, very slow. So in this chapter, we will study about the rate of reaction and how this rate of reaction is, you can say, changes with respect to concentration, with respect to pressure, with respect to other different parts. So, and then equilibrium means whenever, suppose reactant is converting into product, and then product may be disintegrate and convert again into reactant. So there is a situation in which the rate of conversion of reactant into product is equal to the rate of conversion of product back into the reactant. And this situation is known as equilibrium. And we represent the equilibrium with the help of this sign. This is a sign of equilibrium. It means that the rate of change of reactant to product is equal to the rate of change of product to the reactant. Clear?
Yeah.
Any doubt in this? Okay, fine.
No.
Now we will study how fast a reaction. Now some of the chemical reactions are completed within a fraction of a second, whereas other take centuries. For example, weathering of rocks. So weathering of rocks is a physical change, but it will take time. So high explosive detonate immediately and the fireworks shoot upwards, producing amazing display of color and instant the fuse burns down. So there are so many things are there which work immediately. For example, fireworks, they are the immediate. So fireworks over the Tower Bridge in London. So these are the examples of very fast reaction. Whereas rusting is relatively a slow reaction. Good news, if you want to cross the fourth rail bridge, if you want to cross the rail bridge, so it will not rust because rusting is a very slow process. So, okay, clear? Now, what do you mean by the rate of reaction? The rate of chemical reaction measures how fast a reactant is being used up or how fast a product is being formed. So the rate of a reaction is defined as the change in concentration of reactant or a product in a given time. Now see this, I'm opening a PPT there. Now rate of reaction. Now suppose there is a reaction A which is converting into B. So A is the reactant and you are getting B as a product. Now there is some concentration of A. So concentration of A is represented by this square bracket, and initially the concentration is X moles per liter, and B will be equal to 0. Now after some time, or you can say after T time, whenever the reaction is completed, B will be 0, then A will become X mole per liter. So it means whole A is converted into B. Clear? So rate will be equal to concentration of A divided by time. The concentration unit is mole liter inverse, time unit is second. So unit of rate of reaction will be equal to mole liter inverse second inverse. Clear? This is the unit of rate of reaction. Is that point clear?
Yeah.
Any doubt in this?
No.
No? Okay, now you can see change in concentration upon time. Change in concentration means moles per liter cube or moles per decimeter cube inverse second.
So
Yes.
for the change in concentration,
Mm-hmm.
do you have to get like the highest concentration minus the lowest?
Yes, 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 yes. High minus low. Or
Okay.
change in concentration, yes, high minus low. Simple. The rate of reaction is fastest at the start of the reaction as each of the reactant is at the high concentration. Whenever it is starting, the rate of reaction is very, very high as each is in very high concentration. Now the rate of reaction slows down as the reaction proceeds because the reactant are being used up and the concentration is decreased. Always remember that the rate of reaction
Yeah.
slows down as the reaction proceeds because the concentration of reactant will decrease and hence the concentration will decrease. So it means that always remember that that rate of reaction is directly proportional to concentration of reactant. More the concentration of reactant, more will be the rate of reaction. Here,
Yeah.
okay. Now, once the reactants are completely used up, the concentration stops changing and the reaction rate will be equal to 0. You can clearly see the concentration. This is the time. This is the concentration. So concentration is given in mole per decimeter cube. So after some time, it is not changing. It
So
means
at 150 seconds.
yes, at 150 seconds around, after 150 seconds, there is no change in the reaction rate. So it means that there is no change in the concentration. It means that the rate of reaction is 0 at that time. Here,
Yeah.
so this concentration time graph can be used to monitor the rate of reaction. Now, once one of the reactant has been completely used up, the reaction graph changes and the rate of reaction is 0. Now, this is the concentration of product. Now, see, just a bit. Okay, now see this thing. Suppose reaction is there, A is converting into B. Fine. If you see, I'll tell you there are X mole per liter of A, and then B is 0. Now, if I draw, this is concentration and this is time. Concentration is in mole per liter and time is in second inverse. If I draw for the A, now concentration of A will decrease because A is converting into B. Suppose at highest at time t is equal to 0, this is the concentration of A. So it will decrease and after some time it will become 0. So this will be something like this. Is that point clear?
Yeah.
Graph of A will be something like this. Fine. And
Yeah.
B concentration will increase. B concentration will increase. This is the B graph. And this one is for the A. Clear?
Yeah.
Got it? Any doubt in this? But it will increase. Okay. What will happen? I will draw it more clearly. So the concentration of B will increase up to a certain limit. After that, it will not increase. At this position means no reaction. No.
So for the products that react,
At this position, no reaction means whole A is converted to B. This means whole of the A is converted to B. What you were saying, beta?
so for A, it's a reactant. So it says at the start the reactant is at high concentration, so that's
Hmm. Always
so for B it's at low concentration, the
no,
opposite.
B at starting of the reaction, B is not there. Na? We have only A and which is converted to B. At the starting of reaction, we are not having any B.
Yeah.
Because A is the reactant. Are you getting me? What I'm trying to say? So B, suppose you have an N2 plus H2. You are going to produce ammonia. So in starting, you are having nitrogen box and you are having a hydrogen cylinder, nitrogen cylinder. So both are there, but there is no ammonia because they have not started reacting. Initially, you have these two things. Now, as their concentration decreases, then the ammonia concentration will increase. That is what I have already told, that concentration of A, that is the reactant, will decrease and the concentration of B, that is the product, will increase. This is for reactant and this graph is for product. And after some time, you will see that this concentration is not changing. It will remain constant. It means that no more product is formed. If this concentration graph, if concentration of B, or you can say graph of concentration of B is parallel to time axis, it means no change, no formation of B. So B is not formed. Clear?
Yeah.
Okay. चलो जी वापस आ जाते हैं इससे अपना बुक पे. Okay. So one of the reactant has completely consumed. We have done all this thing. So now this is the concentration of B, and after some time the B concentration is not changing. It means that the reaction is complete. Clear?
Yeah.
Okay. Now see. Now figure this 3, this concentration diagram. This shows the formation of product over the, just a second. So we can't do this. Okay. Now if you see figure 3, shows that the formation of product over the course of a chemical reaction. So this graph is for the product graph, which is showing how the product is formed during a chemical reaction. The slope of the curve is the steepest at the start of the reaction when the rate is great. If you see, this curve is very, very steep at the beginning because at the beginning the rate of reaction is high, and as the time proceeds, this curve will become parallel to time axis because it means that the reaction is not there, that the reaction is complete and the rate is equal to 0. Is that point clear?
Yeah.
Okay. Now, how you can alter the rate of chemical reaction? Or you can say factors that can change the rate of a chemical reaction. The first factor is concentration or pressure. Concentration in terms of a liquid and solid one, and the pressure in terms of a gases. Then second example, we have temperature. Third is we have use of catalyst, and the fourth we have use of surface area for a solid reactant. Okay, to understand why the rate changes, we need to understand about the reaction in terms of particles involved, that is the collision theory. So as per the collision, okay, so these are the things which change during the, or you can say which can change the rate of chemical reaction. If suppose more amount of A is available, then more will be the change of reactant. If more amount of reactant is available, it means the rate of reaction will be more. Clear? Now suppose temperature. Now suppose temperature is high, then the kinetic energy will increase and hence the rate of reaction will increase. Use of catalyst. Catalyst will increase the rate of reaction, or it will make the reaction a little bit more fast. In the surface area, more the surface area, more will be the rate of reaction. Example, if you need to burn any, if you have a, sorry, if suppose if you have a big log of wood Now, like this bigger log of wood is there. So you can't just you can say put this log of wood in on fire with the help of a single matchstick. But if I convert this log of wood into a small particles, that is in a saw, I just powdered in the powdered form. So in a powdered form, if you use this matchstick, it can easily catch fire. So in this way, all these things can alter the chemical reaction or rate of chemical reaction. Here,
Yeah.
okay. Now to understand why, okay, the collision theory states that two reacting particles must collide for a reaction to occur. Now, as per the collision theory, what is there? Suppose these are the two particles. For a chemical reaction, these particles should collide. If they collide, then only there will be a chemical reaction. The only a small proportion of collision results in a chemical reaction. Now, in most collisions, the molecules collide, but when they bounce off each other, they remain chemically unchanged. So, there are some collisions which are effective, and there are some collisions which are ineffective. Only effective collisions are the one which lead to a chemical reaction.
Yeah.
Okay. Now it is more like suppose, uh, have you ever played darts? Do you वाला game खेला कभी dart वाला game? Have you ever played dart game? You throw a dart
Yeah.
and you have to put it center. Suppose this is a 10 pointer, this is 9 pointer, 8 pointer, 7 pointer. So you throw so many darts, but not every dart will move at this 10 pointer now.
Yeah.
So it means you are throwing, it means collision is there, but not every collision will result in the 10 pointer. In a similar manner, every particle is colliding with each other, but it doesn't matter that all the collisions are effective. There are more ineffective collisions, but there are some collisions which are effective. If there is an effective collision, then only a chemical reaction happens, or you can say a new product is formed. You can see in this is a molecule and this one is the other molecule. So they are colliding with each other, and the result is not giving you any new product. It means collision is there, but this collision is ineffective. Yes. Again, these two molecules are reacting with each other, but somehow there forms these two different products. Now this is known as the effective collision. So this is known as collision theory. So collision theory states that whenever you can say two particles need to collide in order to occur a reaction. Now this collision can be of two types, the effective and the non-effective one. Only those collisions in which a new product is formed are known as the effective collisions, and they only occur a chemical reaction. So a collision will be effective if there are two conditions that have been there. The first one, the particles collide with the correct orientation. Now collision will be there only whenever there is a correct orientation. And the second point is the particles will have sufficient energy to overcome the activation energy barrier of the reaction. Now suppose you are throwing a dart. Okay, now if you see the dart, it is something like this. Something like this. Yes or no?
Yeah.
Okay. Now if you throw a dart, if this position is towards your target, then only it will collide.
Yeah.
If you are throwing with the back side, then it will not get stick to it. It will not get into it.
Yeah.
Okay. It means you need a correct orientation.
Yeah.
Clear? Okay, Ji. And you should throw this such a speed that it should get into it. It should get stuck into it. Otherwise, it will not get stuck into it. Huh?
Yeah.
It will fail. So both the things should be there. It means that there should be a correct orientation of particles for collision, and there should have a sufficient energy to overcome the activation energy barrier for a reaction. And if these two things are there in a collision, then that collision is the effective collision, and it will result in a formation of product, or it will result in the chemical reaction. Is that point clear?
Yeah.
Sure, Pakka?
Yeah.
ठीक है जी. You can clearly see in this case and in this case no reaction, but this is going to give you reaction. So two blue atoms collide and form a new product. And this is known as effective collision because it is having the correct orientation of collision, and it also has a sufficient amount of energy to overcome the activation barrier of a reaction. Okay. Now, how to increase the concentration rate of a reaction? It means how to increase the concentration effect of a rate of reaction. Now, suppose concentration, how the increase in the concentration affect rate of reaction. Now, concentration of reactant. Now, as per the collision theory, there should be a collision so that it will react. There should be some collisions so that it can react. Now, number of collisions will be equal to whenever we have more number of collisions. When we have more number of reactants, so more number of reactant are there, it means more the number of collisions.
Yeah.
So it means more concentration means more reactant, and more reactant means more number of collisions. So in this way, we can say that the concentration is more, if the reactant concentration is more, then more will be the rate of reaction, or more the chances of a reaction to occur. Now, when the concentration of reactant is increased, the rate of reaction generally increases. An increase in concentration increases the number of particles in a same volume, and if the number of particles are increased, the chances of getting the effective collision will increase. The particles are closest together and they collide more frequently. And in a given period of time, there is therefore a more effective collision. That is, the correct orientation particle with sufficient amount of energy can happen, and an increase in rate of reaction will occur. Is that point clear?
Yeah.
Any doubt?
No.
Okay. Now you can clearly see in this the marble chips in different concentration of acid. The highest concentration on the left hand side, the lowest concentration is on the right. This is the lowest concentration of acid. This is the highest concentration of acid. You can clearly see more the concentration, more amount of marble chips will react, and you can't see any marble chips. But in this too, you can clearly see the marble chips because the concentration is less, so the rate of reaction will be also less. Clear?
Yeah. Yeah.
So it means as the concentration increases, the faster will be the rate of reaction. Why it happens? Because of the collision theory. Because as the number of concentration increases, it means more number of particles are there in the same volume, and more number of particles means more, you can say, probability of colliding with each other. The frequency of collision will move, and hence we can have a more number of effective collision in a period of time, and hence it will increase the rate of reaction. Clear?
Yeah.
Okay, Ji. Now, how an increase in pressure of a gas affect the rate of reaction? Now, suppose this is a bucket and this is a piston. It is having a volume. This is volume B. This is a volume B. Now, if I put some pressure over it, what will happen? This will shift below. Clear?
That will, yeah.
This will shift below.
Compact.
It will become compact, and the volume decreases. You can clearly see that the volume will decrease. Now, the amount of particles is now there in the lower volume. If number of particles remain same and volume will decrease, it means more amount of, you can say, particles will collide with each other.
Yeah.
If they are colliding with each other, that is a more the probability of getting effective collision, and hence the rate of reaction will increase. Clear?
Yeah.
So when a gas is compressed into a smaller volume, the pressure of a gas is increased and the rate of reaction increases. The concentration of the gas molecule increases as the same number of gas molecules are now occupying the smaller volume. The gas particles are more closer to each other and collide more frequently, leading to the effective collision in the same time. Got it? Clear?
Yeah. Yeah.
So because of this, we can say that more the pressure of a gas, so more will be the rate of reaction. The method for the following the progress of a reaction. The progress of a reaction can be followed by first part, monitoring the removal, that is a decrease in the concentration of reactant, or monitoring the formation, that is formation of the product. Now we know that A is converting into B. So A is a reactant. So with respect to time, the concentration of A will decrease, and with respect to time, the concentration of B will increase. So we can monitor any rate of reaction or any chemical reaction with the help of two things. That is how you can say how frequently or how quickly the reactants are disappearing, or the decreasing concentration of reactant. Or second way is how quickly or how you can say how fast the rate of formation of product. So monitoring the removal, that is decreasing the concentration of reactant, and monitoring the formation, that is the increase in the concentration of product, are the two methods to understand about the progress of a chemical reaction. If you remember this paragraph, this graph. Now this graph is for the product. After some time, it is parallel to time axis. It means the reaction is now finished. There is no further change in the product. It means all the reactants is finished. Now if you see this concentration is 0, it means there is no reactant. Each and every reactant is converted into product. Clear?
Yeah.
Okay. So the method chosen will depend upon the properties and the physical state of the reactant and the product of the reaction. In addition to the concentration, measurable properties might change as the reaction proceeds, including gas volume, mass of reactant or product, and color. Now, because of this, sometimes we can make it sure with the help of pressure, with the help of color change, with the help of reactant or product mass, and also all these things can help us to tell us about whether this change might be a chemical or not, whether the change is finished or not. Okay.
Yeah.
Okay. Now we will see reaction that produces gases. Now, if a reaction produces a gas, the two methods can be used to determine the rate of reaction. The first one is monitoring the volume of gas produced at the regular interval of time using gas collection. And the second one is monitoring the loss of mass of reactant during using a balance. Now, if suppose one of the product is forming a gas, now how you can predict the rate of reaction is there, or how you can determine the rate of reaction? The first one is we can monitor the volume of gas produced at regular interval. So after every 5 seconds or every 10 seconds, we can collect that what amount of gas is produced. Now, as the amount of gas after some time, if it is decreasing, it means the reaction is going towards the completion. Now, suppose in first 10 seconds, we got 10 ml, 10 volume of 10 centimeter cube of gas. Now, after 10 seconds, we get 8. After 10 seconds, we get 6. After 10 seconds, we get 3. Or after 10 seconds, we are not getting any amount of gas. So it means the reaction is finished. So just by monitoring the volume,
like, so you just have to collect the amount of gas,
yeah, obviously,
like measure it at like tiny intervals.
Yes, we have to collect it, then only we can measure, no?
Yeah.
Without collection, how you can measure? As soon as it is moving out, you have to measure it, whether it is there or not, how much amount of it is collected. Now, with respect to time, we all know that the product is going to form less. So in this way, we can say that after some time, the volume will be less. Clear?
Yeah.
The second is monitoring the loss of reactant, or we can predict, or we can say the A is converting into B. Now, this gas formation is there with the expense of reactant. As the reactants are reacting, as they are producing some gas, so their mass will decrease. So we can also check what amount of mass is decreasing in case of reactant. If the mass is decreasing much, it means there is a completion of reaction. If no reactant is there, it means the reaction is fully finished. The volume of gas produced and the mass lost both are proportional to change in concentration of reactant or product. If there is no amount of reactant available, then the product is found maximum. Then there will be no reaction. The rate of reaction is finished. So the change in the volume with the time or the mass lost with time both give a measure of rate of reaction. Clear? So we can
Yeah.
say that the rate of reaction, or there is a disappearance of A concentration, and there is the occurrence of or formation of B. So the change in the volume with time or the mass loss with the time both give a measure of rate of reaction. Clear?
Yeah.
Any doubt?
No, it's fine.
Fine. So you can see this monitoring the production of gas using a gas collection method. This is known as the downward displacement method. In this reaction, gas is produced. Now, gas is produced in form of a bubble and over there. So initially, it was like this. As the gas is produced, it will make the whole. You can say it will put the water down, and hence there now this much amount of gas is there. The whole. Clear?
Yeah.
This is a chemical reaction which H2O2, that is peroxide, reacts in the presence of MnO2. It is giving you water and O2. So this is the oxygen gas collected. So the rate of decomposition of hydrogen peroxide can be measured by using the apparatus in figure 7. Now, as the amount of O2 is formed, we can measure whether the reaction is complete or not. So hydrogen peroxide, you can also measure the hydrogen peroxide. The amount of hydrogen peroxide will decrease and this amount will increase. So with the help of increment of oxygen gas and the decrement of hydrogen peroxide, we can determine about the completion of rate of reaction. The initial volume of gas is measured in the cylinder, is recorded. Then after some time, we measure the record. And that by measuring these records, we can clearly find out whether it has been finished or not. So some sort of this type of graph is there. Now this type of graph, if you see blue graph, after 60 seconds, this graph is becoming parallel to time axis. It means the reaction is full. The reaction is completed. Clear? And this at this position, if you're drawing a tangent to it, this tangent is giving you the instantaneous rate of reaction at that time. Clear?
Yeah.
Okay. So this graph of volume of gas produced against time. So this is the amount of gas produced with respect to time. Clear? Now, in this case, working example is there. Calculation of reaction rate from gas produced. Now, whatever the amount of gas is produced, you need to calculate the reaction rate. Now, plot the graph of volume of gas produced against the time. That is figure 8. Figure 8 is, okay, now this is the graph. You need to plot graph like this. Now draw a tangent at t is equal to 0. And from t is equal to 0, you need to draw a tangent. This tangent is there. At t is equal to 0, red line in figure 9. And this is known as initial rate. This is the initial rate of reaction. This red line is giving you the initial rate of reaction. Now calculate the rate from the gradient of the tangent. The rate of reaction will be equal to y upon x-axis. Y upon x-axis. So x-axis is this change. Okay, x-axis is this A. For y-axis, it is 120 and 40. So 120 minus 40. And for x-axis, it is this and this. That is 24 minus around 8. So 120 minus 40 divided by 24 minus 8, you will get 5 centimeters per second. This is going to be the rate of reaction. Clear?
Yeah.
Any doubt?
No,
So you need
it's
to
fine.
okay. Now you need to now calculate the rate of reaction after 24 seconds and 40 seconds. You can do this as a homework. Got it?
Yeah.
Okay. Now you can use the following method also, that is monitoring the loss of mass of the reactant using a balance. Now as the reaction proceeds, the reactant will decrease, the mass of the reactant will decrease. Now if you see, initially the mass is 193.49. Now the mass is 193.19. It means 0.30 amount of CaCO3 or 0.30 amount of that particular substance is used in making the gas. So as the mass is lost, it means that the gas is produced. For example, in the case of CaCO3, calcium carbonate when reacts with HCl, it will produce carbon dioxide. So the rate of reaction between the calcium carbonate and hydrochloric acid can also be used to determine the monitoring of loss of mass reacted over a period of time. The reaction is something like this.
There is a loss in the mass of
reactant
calcium carbonate.
Yes, the calcium carbon is a reactant, huh?
And then
which means that
so then there's a loss in the reactants, that means so for the volume of gas there's an increase.
Yes, very good. More the amount of reactant is consumed, then more the amount of product is formed, right? If it is something like that, more amount of sugar you will dissolve, more sweeter you will get.
Yeah.
The same thing, more amount of reactant is consumed, the more amount of, you can say, product is formed.
Yeah.
Yes, or more, you can say the more the loss of mass of reactant, more the product is formed. Clear?
Yeah.
Got it?
Yeah.
So the carbonate and the acid are added to the conical flask on a balance like this. The mass and the flask of the content are recorded initially at regular interval of time. The reaction is complete when no more gas is produced, so no more mass is then lost.
So then the calcium carbonate doesn't, so it's still like it stopped reacting, so it doesn't lose.
Yes, after some time, it means the mass will not change. It means no further gas is formed.
Okay.
The graph of the mass of the loss is again plotted. So it will be something like this. And if you draw a graph at this point, this will be giving the tangent or the rate of reaction at this point. And if you draw it from there, it will give the rate of reaction at initial concentrations. Here at time t is equal to 0, and this is giving you at time t is equal to 100 seconds. If you want to check it for the graph at time t is equal to 150, then you have to draw something like this. Here?
Yeah.
Okay. This will be. Okay then. Got it? Any doubt on this?
Just another question on tangents. Like they're only drawn when there's a curve.
You know what is tangent? Tangent is a line outside the circle which touch the curve at only one single point. Now, if you see, okay, now plot the loss of mass curve. This is the loss. This blue line is the loss of mass. Okay, you can clearly see the loss of mass is there. It's coming down. This is the loss of mass. Now, initially at this position, if you draw it, the loss of mass is from 0 to -6. So on y-axis, it is 0 minus -6. So it will become 6. And from this to this position, it is coming at t is equal to 70. So 0.6 by 70 is equal to 8.6 into 10 power minus 3 gram per second inverse. This is the rate of reaction. Now calculate the specific reaction time. That same tangent method is used in figure this one. The orange tangent is used. Now this is the specific reaction rate. Means at this point, again you draw a tangent. Now this is this one, and time is this. So we have around 0.25. So this will become 0.36. This is 0.36. So y is 0.36 divided by 110. You will get 1.7 10 power minus 3 gram per second inverse. So we can say the rate of reaction is also decreasing with respect to time. With the increase in time, the rate of reaction is decreasing as the product is formed less. As a product is forming less, or as a product is forming more, and the concentration of CaCO3 is decreasing. Clear?
Yeah.
Any doubt?
No.
Okay, so a chapter is finished. Do one thing, just quickly read this again, okay, and then do these questions.